Okay, welcome to ePortfolio Project 2. This is chapter summary for chapters 4, 5, and 6. We're going to start with chapter 4. Okay, so the first main subject that we touched on in this chapter was the subject of boundary work. Alright, which I'm going to denote by WB, and that is equal to the integral of capital P dV, which is equal to m mass times the integral of capital P little dv, depending on which variables you're given. So we know that WB, if it's constant pressure, is equal to P times V2 minus V1. Simple there. If it's a linear increase in pressure, WB is equal to P1 plus P2 all over 2. So you take the average of them, more or less. V2 minus V1. If it's a constant temperature, ideal gas, it's WB equals P1 V1 times the natural log of V2 over V1. And if it's polytropic, boundary work is P2 V2 minus P1 V1 all over 1 minus N. Okay. Still in chapter 4. The next topic is the energy balance for a closed stationary system. Keyword here is closed for chapter 4. So that energy balance formula, E in minus E out equals delta E of the system, is going to equate to this: Q in minus Q out plus W in minus W out is equal to delta U. Since it's a stationary system, there's not going to be that potential energy or the kinetic energy taken into account in that. So just remember that. And also remember that if it's expansion, the work is going out. If it's compression, the work is going in. So compressors, they're work storage devices. Turbines, work delivery devices. Okay. The next subject is that the change in enthalpy for a constant pressure process, or delta H, is equal to delta U plus the boundary work. Okay. So we can interchange that. That proves convenient frequently when we're trying to convert from internal energies to enthalpies, or vice versa, given the variables that we have to work with in our problem. Alright, the next important topic from chapter 4 is going to be specific heats. So CP is specific heat at constant pressure, and CV is specific heat at constant volume. Okay. And just that we want to remember our relationships for ideal gases. Du equals CV as a function of T dt. DH is CP dt. R, our gas constant, is derived from CP minus CV, and K, which is CP over CV. So that kind of covers specific heats. So we can use specific heats to go back and forth using that CV dt relationship and CP dt equal to change in internal energy or the change in enthalpy, respectively, to move back and forth given specific things that we know or don't know in our problem statement. So that pretty much sums up chapter 4. All right, moving on to chapter 5. Okay, so the first main point, I guess, from chapter 5 was conservation of mass for a steady flow process. So we want to remember that if it's steady flow, that the sum of the mass flow rates of the inlets are going to equal the sum of the mass flow rates of the outlets. Okay, so if we had, for example, a situation like this, we're going to have m.1, m.2, m.3, m.1 plus m.2, our inlets are going to equal m.3, which is our outlet. Okay. And also we want to remember from earlier chapter that m dot, or mass flow rate, is equal to density times the cross-sectional area times the velocity, or density is equal to our volumetric flow rate, or V dot. So, the next subject for chapter 5 is going to be the rate of energy transport by a mass. So, our energy mass, or E mass, is going to equal m dot H, internal energy, plus V squared over 2, our kinetic energy, plus Gz, our potential energy, times mass flow rate. So, anyway, and keep in mind that the relationship of H is equal to U plus PV, our boundary work. So our flow energy and our internal energy. But most of the time we're just going to worry about the change in enthalpy. Alright, the next topic for chapter 5 was our all-important energy balance for, this time, drum roll, an open system. Remember, chapter 4 was for a closed system. This is for an open system. So this is the big long one that we want to write down every time to make sure we don't mess it up. So we're going to have Q dot in plus W dot in plus the sum of the mass flow rates of the inlets times H plus V squared over 2 plus Gz is equal to Q dot out plus W dot out plus the sum of M dot H plus V squared over 2 plus Gz again. So, and then keep in mind that little q is equal to Q dot over M dot, depending on what they're giving you for the problem. So this is the main equation that we used all the time in chapter 5, and frequently we'd be canceling different things out. So we talked about some different devices and control volumes. Remember, our control volume and establishing that is very important with an open system. If we don't establish the correct control volume or don't define it, you're going to have a hard time getting the problem right. We talked about nozzles and diffusers. Nozzles speed up, the velocity increases. Diffusers, the velocity decreases. We talked about turbines, work producing devices, compressors, work storage devices, and pumps. And then also throttling valves, mixing chambers, and heat exchangers. So, and then lastly, our ideal gas assumptions. So one more time, our delta H equals Cp delta T, and delta U equals Cv delta T. Our ideal gas equation, PV equals RT, yet again. So that pretty much sums up chapter 5. Now we're going to move on to chapter 6. So in chapter 6 we talked about the second law of thermodynamics, and just that processes more or less occur only in a certain direction. Work can be completely converted into heat, but not vice versa. So we can't take that work and go back. So, and then the Kevin Planck statement, any work-producing device that receives heat from a single source and operates on a cycle must reject heat. Keyword must reject heat to complete each cycle. So we talked about refrigerators and heat pumps and heat engines in this chapter. So refrigerators, the desired output is going to be our cold refrigerated space, or TL. Our work is coming in to the system, and then it's rejecting our QH, or our heat that's going out back into the warm environment. So the opposite is true for a heat pump. Our cold outside environment is coming into the system, and then work's coming in and it's putting the warm air out into our desired heated space. So we talked about thermal efficiency and COP. So efficiency, which we're calling eta, which is similar to COP with refrigerators and heat pumps. Remember that efficiency is for heat engines, COP is heat pumps. It's going to be our desired output over our required input. So for heat engines, it's going to be the work out over QH. For refrigerators, COPR is QL over W in, and for heat pumps, COPHP is equal to QH over work in. Okay. We also talked about irreversible, reversible, and impossible cycles. Remember, in nature, everything is irreversible, but for some things they can be modeled as reversible for the sake of solving the problems. So, for heat engines again, the way of writing it is 1 minus TL over TH. For refrigerators, it's 1 over TH over TL minus 1, and 1 over 1 minus TL over TH for heat pumps. And lastly, we talked about the Carnot cycle and the PV diagram of the Carnot cycles, and how those are totally reversible. So anyway, this concludes our chapter summaries for chapters 4, 5, and 6. Thanks for listening, and we'll see you later.